Ever stared at an ultrasound image and thought, why does this look like a grainy photo from the 90s? That's speckle noise, those tiny, random patterns that obscure critical details in medical scans. But here's the breakthrough. Scientists have cracked a code to make these images crystal clear, and it's all thanks to a revolutionary technique called Speckle2Self. Let's dive into how it works, and why it's a game changer for medical imaging. So how do ultrasounds actually create images? They send high-frequency sound waves into the body, which bounce off tissues and return as echoes. The machine translates these echoes into visual data. But here's the catch. Those sound waves interact with microscopic structures, creating a unique fingerprint of noise. Unlike TV static, this speckle isn't random. It's a signature of the tissues themselves. That's why old-school methods like basic filters or naive AI fail. They either blur vital details or leave the noise untouched. Traditional approaches. They're like trying to fix a photo with a sledgehammer. You need clean images to train AI, but real-world scans are always noisy. It's like learning math with a textbook full of errors. That's where Speckle2Self steps in. Instead of relying on perfect data, it uses a clever trick, multi-scale perturbation. Imagine taking a single ultrasound image and generating multiple slightly altered versions, each with unique speckle patterns but the same underlying anatomy. By analyzing these variations, the algorithm learns to distinguish real tissue from noise. It's like training a detective to spot a suspect's face in a crowd by comparing multiple blurry photos. The key. The algorithm treats the image as a low-rank structure, the core details, and isolates the sparse noise, the speckles. Here's the magic. The algorithm doesn't need a clean reference image. It creates its own by perturbing the original at different scales. Think of it as shaking a photo at varying intensities. Consistent features like organ boundaries stay the same while speckle changes. By comparing these perturbed versions, the system identifies which patterns are stable tissue and which are erratic noise. It's like teaching a computer to recognize a tree by analyzing its leaves, branches, and trunk at different resolutions. The results? In tests, Speckle2Self outperformed traditional methods and even worked on real-world scans from human carotids. It's adaptable, too. It doesn't need special hardware or extra data. This means it can run on standard ultrasound machines, making high-quality imaging more accessible. Why does this matter? Beyond cleaner images, Speckle2Self enables advanced applications like elastography, measuring tissue stiffness, blood flow estimation, and echocardiography. For example, it could track micromovements in heart tissue or detect abnormal stiffness in organs, a critical tool for early cancer detection. Plus, its data efficiency means it thrives in low-resource settings, where portable, low-cost ultrasounds could save lives. So next time you see an ultrasound image, remember, behind that grainy surface is a world of innovation. Speckle2Self isn't just about making pictures prettier. It's about unlocking deeper insights, improving diagnoses, and bringing cutting-edge care to places that need it most. The future of medical imaging isn't just clearer, it's smarter.